Okay, so today we'll solve mathematics GATE 2023 question. This is a question from functional analysis. It is question number 37. It is saying that let L2, this is be this sequence space where this is a square summable sequencer. So and for a sequence in L2, small L2 basically, the norm is basically take the square sum to the power half. Then two linear operators are defined, S from both the space from L2 to L2 and T is again from L2 to L2. S is defined like this and T is defined by this. Then you have to check, the four options are given. It's saying that S and T are, you have to basically check that this is compact linear operator or not, right? Okay, so in order to solve this problem, this is the NPTEL reference. Okay, so let's start. So let me first give the what is compact linear operator. So let X and Y are two Banach spaces. Means they are basically complete non-linear space. An operator, linear operator, T from X to Y is called compact operator if, means it will take basically the unit ball, if the take T image of this unit ball where B01 is the unit ball, take the closure, this should be compact in Y basically, because it will map to Y. So the closure of the image of the unit ball should be the compact. What is the unit ball? This is basically B. So this is the definition for the compact operator. What is B01? So this is basically all such X in X such that norm of X. So this is norm in the space X less than equals to 1. Right. And as this is a linear operator, so if it is mapped the closed unit ball to the, it will take the any bounded set, right? So basically this is equivalent again. Equivalent definition. What is the equivalent definition? So T is called compact basically not for unit ball, if any bounded set, if image of any bounded, so closure of the image of compact if T of A closure is compact, where what is A? Where A is any bounded set in X, right? So this is basically in Y. So this is means basically if you take any bounded set, take the image, apply T, and whatever we will get the image, take the closure. If this is compact, then it is called that linear operator is compact operator. Again there is another equivalent definition. So this is definition 1. So this is same as take any bounded sequence and see what will be the image of that sequence. If so, the closure should be compact, means if that sequence has a convergent subsequence, then we can say that T is again compact operator. Again saying that, so T is compact if and only if for each bounded sequence xn, the sequence T of xn has a convergent subsequence. Right. So we'll call T is a compact if for every bounded sequence xn, so the sequence T xn has a convergent subsequence. So this is a very useful criteria in order to check that an operator is compact or not. So you will use this one. So let me, so this we will use basically, right. Okay, so two operators are given, S and T. What is S? Here first let's do it for S. S is a operator from L2. This is a sequence space with this L2 norm to again L2 so it will take a sequence x1 x2 dot dot dot, and how it will map, it is y1 y2 dot dot dot, where what is yn, where yn is 0 if n is 1, and it is basically x n minus 1, right, if n is 2. So how it will look like, basically s of x1 x2 dot dot dot. So y1 is always 0, and what is y2? Y2 is x1, y3 is x2, right? So it basically shifts one places, right, in the right. So that's why S is called right shift operator. So this is called the right shift operator. So you have to check that this right shift operator is compact or not, right? So we'll use the last characterization. So you have to find a bounded sequence, so that we have to check that this S of that sequence has a convergent subsequence or not. So we'll show that this S is not a compact operator. Claim. So let me claim. S is not compact operator. So means you have to find a bounded sequence so that S of En does not have any convergent subsequence. So what will be the choice of our bounded sequence? So let's take the sequence to be the En. So this is in L2, right? Why? What is En? Ens are basically 0, 0, dot, 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 0, 1, 0, dot, 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 dot. Where 1 is in the nth place. right? So basically this is from n greater than equals to 1. This is a sequence. So like this u1, it will be 1 0 0 dot dot dot, e2 is 0 1 0 0 0 now, like this. So clearly these are in L2, right? Because only one term is non-zero here. And note that what are the norm of this En? So L2 norm, so this is n greater than 1. What is xn? So only one term is there to the power of, so basically norm is 1 for all n greater than 1, right? So therefore ens are bounded, right? Because all has norm 1. So en for n greater than 1 is a bounded sequence in L2 with respect to this little L2 norm, right? Now we have to apply S on this sequence. So note what will be this S of En. What S does? S basically shift by in the right by 1 place, right? So it will basically, what it will be? So S is basically S of 0 0 0 0 0 0 1 0 0 0 0, right? So it will shift by 1. So here it is nth place, then 0 0 0 0 0, it will be 1, like this. Here it will be n plus 1th place, right? So basically this is En plus 1. So S takes En to En plus 1. So therefore this S of En, you have to check that this for n greater than 1. So this is basically En plus 1. It has a convergent subsequence or not. So we will prove that, therefore we will show that this does not have any convergent subsequence, right? Why not? So if not En plus 1 for n greater than 1 does not have any convergent subsequence. Why? Because if it has any convergent subsequence, then that subsequence must be Cauchy, right? Every convergent sequence is Cauchy in Banach spaces. So now, so therefore let's check what is En minus Em in this L2 norm for m not equals to m. So therefore it is basically contain two terms, right? Only plus 1 and mod of minus 1, right, to the power half. So this is basically 1 plus 1 is 2 root 2. So for n not equals to m, note that distance of En and Em is always root 2, right? So for any n not equals to m, it is at distance always root 2, so it cannot goes to 0, right? So therefore En plus 1 for n greater than equals to 1 does not have any convergent subsequence. Right, because if it has a convergent subsequence, that subsequence must be Cauchy. So therefore E that for two different indices, that difference must go to 0. But as we have shown that this is for any different indices, it is always root 2, so it can't go to 0. So therefore S of En cannot have, let me write it here, S of En does not have any convergence subsequence, means S is not compact, which implies S is not compact operator. Right. Okay, so for S it is done. Now what is T? T takes to this. For n odd it's 0, n even it's xn. So claim again, so we'll prove again that T is also not compact operator. So claim T is not compact. So what is T? T basically take L2 to this to T of x1 x2 dot dot dot, it will map to y1 y2 dot dot dot, where yn is basically 0 if n is odd, and this is xn if n is even, right? So basically if you will take any sequence, it will send it to, or in odd places it will be 0, and it will be the xn for n nth places is even. So in order to show that this is not compact, again we have to find a bounded sequence so that T of that bounded sequence does not have any convergence subsequence. So again, as earlier we will take, so let's take that sequence to be, now this time take E2n, we will take only even E2n, where ENs are as early, right? 0 0 0 dot 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 1 0 0, like this in the nth place. So means E2n, these are 1 in the even places, 2 nth places, right? For n greater than 1. Then what will be T of En? T of E2n T 0 0 dot 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 0 1 0 0 dot dot dot. So this is basically 2 nth place. How it will map? In the all odd places it will map to 0, and even places here it is all 0 0 0 0. Because 2n is even, it will map again it to 1 because it is xn, and even places other 0. So it will basically map the same. So E2n, it will map to E2n for all n, right? So T of E2n, it will map to E2n, right? And again, what is the norm of E2n? L2 norm, as early this is again norm 1, right? So therefore E2n is a bounded sequence in L2. Now again you can check that. So claim means, note that as early again T of E2n for n greater than 2, basically this is the En again, E2n. This does not have any convergence subsequence. Any convergence subsequence. Why? Because this is as earlier reason that for any m not equals to n, or any m not equals to n, norm of E2m minus E2n, L2 norm, this is again you will get root 2. So therefore it cannot have any convergence subsequence, right? Because it has then again that will be Cauchy, means that difference should goes to 0. So which implies T of E2n for n greater than 1 does not have any convergent subsequence. Which implies that T is not compact operator. So we have get that S is also not compact operator and T is also not compact operator. So which option is correct here? S is compact operator, first option is false, B is also false, C is also false, so D is correct. Neither S nor T is compact linear operator. So option number D is correct. Okay.